Young Faculty Award in 2016, the Pat Goldberg Memorial Award from IBM Research in 2011, the IBM Research Fellowship in 2005, and the National Talent Search Scholarship from the Government of India between 1995 and 2000. He serves as an associate editor for IEEE Journal of Solid State Circuits. He has also served as an associate editor for IEEE Transactions on Microwave Theory and Techniques. Since 2019, he has been part of the leadership team at Mixcom, which is a venture capital funded semiconductor startup focused on the integrated transceivers for 5G and satellite communication. The Cybers Semiconductor has acquired Mixcom in February 2022. So now we are really honored to have such a prominent person which is having so many awards and has achieved so much during his career to deliver a talk through our chapter. And without any further delay, I will hand over the presentation to Professor Arun. So let's start, sir, if you are ready.
Thanks, Soham, for that very flattering introduction. Really appreciate it. Also appreciate the invitation to talk at what is the beginnings of your student chapter at IISc. Of course, the institution is a institution with a long tradition, and it's really exciting to see the Microwave Society gain a foothold there. So really happy to see this, and I wish you all the best of luck in keeping the student chapter going. And for the audience, I should also say that being part of the student chapter brings with it several resources, access to the IEEE websites, a lot of tutorials, and in general, so I run a student chapter at Oregon State, and I will say that it's a very beneficial thing for the students, so I highly encourage you to participate in this. So today's talk, it's titled out of many, many, so you'll see the reasons for the title as we go along in the talk. But this is not focused so much on research as rather an introductory talk in the field of beamforming and millimeter wave arrays in general. So I will spend a fair bit of time to provide an introduction. Again, I'm keeping in mind a broad audience. While Soham said, to hold questions at the end, I'm fine if you do ask questions in the middle as well. So Soham, feel free to interrupt me if people post questions in the chat. Happy to answer as we go along, but would be grateful if you could monitor the chat since I can't see it.
Sure.
Soham gave my background, but yeah, so I was born in North India. My dad worked in the Indian Railways, so have spent a lot of time in several places, including Mysore. And then did my undergrad at IT, and after bouncing around a couple of places in the US, have been at Oregon State for the last 10 years, where I'm a professor now. And this is the town. It's a very beautiful college town located on the banks of the Willamette River, one of the two rivers that runs north-south along with the Nile, and south to north. And this is the building where our labs are. So it's a really nice place. And if anyone's in the vicinity, please come and visit us. This is the lab students whose work I'll be presenting towards the end. We run a high-speed integrated circuits lab. And Oregon State has a long tradition in mid-signal circuits as well. So there's just a lot of circuits work going on at the university. We have about 9 professors working in the area of what we call integrated electronics. My own research is, I was looking for a theme, and there is this article I once read by David Pogue in the New York Times, which said wireless is magic and magic is happiness. He was describing something very mundane like a wireless USB mouse. But it spoke to me, and I think in general, we take it for granted, but it is really quite amazing the technology that has gone into wireless communication and sensing over the last several years. And my own research now is focused on 3 areas. At RF, we look to build interferer-tolerant reconfigurable radios to support radios operating across multiple bands. At millimeter wave, we work at high frequencies where we are trying to build communication and sensing systems with area and power efficiency. And finally, we also work on sensors where we are trying to build very, very low power sensors that are either RF powered or powered by energy harvesting. But a common theme is that we focus on breaking trade-offs between power and performance. So that is the main area of focus here. So in this talk, I'll first begin by providing the motivation for integrated millimeter wave arrays. And the reason is quite simple. The spectrum from 2 gigahertz to 6 gigahertz is quite crowded already. We can't get really wide spectrum available there. And if we want to increase data rates by going to multiple elements, what we find is that the physical size of the system constrains the number of antennas that we can put in. If we move to higher frequencies, or what we call the millimeter wave carriers, from about 30 to all the way to terahertz at 300, what we find is that we can get large fractional bandwidths. There are large amounts of spectrum, for example, 7 gigahertz of spectrum available at 60 gigahertz. And the physical size of these systems is quite small because antennas need to be spaced only about millimeters apart. So you can have a multiple antenna array fitting form factors like phones and tablets and laptops. So if you take the latest generation of the iPhone, for example, it includes millimeter wave radios along its edges, right? And it also includes a SATCOM radio that's operating at high frequencies. So these systems are getting translated in practice. And what is the key challenge here? Why is it hard to go to high frequencies? Well, when we build a link, we typically think about it in terms of the link budget, which is basically for a given transmit power, there is a certain distance that we would like to reach. And we want to make sure that the power that is incident at the receiver has enough signal to noise ratio that we can demodulate our signal without introducing error. So we consider the link budget at millimeter wave frequencies, and we can write well-known, equations for these link budgets. But effectively, what we find is that we can reduce the noise that is there in the receiver to a single number, which we call the noise factor of the receiver, which sets what is the SNR that we'll get at the input of the receiver. So based on this SNR, we can define what is the minimum input power that we need. And again, just to build some intuition here, what we can show is that for a typical millimeter wave link, we need something that is of the order of the noise is of the order of minus 77 dBm. So we need something that is of the order of minus 57 dBm. So minus 60 dBm, this is all in log scale. So minus 60 dBm, as we know, is about 1 nanowatt. So this is about 2 nanowatts of incident power. So we at least want 2 nanowatts of power incident on our receiver. And now, knowing this equation and knowing the free space path loss equation, we can come up with how much power we need to generate at the transmitter so that we at least see the targeted 2 nanowatts at the receiver, right? And when we make this path loss equation, what we find is that the loss that we see is inversely proportional to wavelength. So the smaller the wavelength, the more the loss that we see. And at 28 gigahertz, which is a popular frequency for 5G, for example, the loss that you would see for a 50-meter link is of the order of minus 95 dB. Or another way to say it is that we lose 10 to the power more than 10 to the power ninth of the power by the time we go through air and it is incident on the receiver. Now I say lose right now, but this power is not lost anywhere. In reality, what's happening is that it is being radiated in all directions, and only a small fraction of the power that we are generating is hitting the receiver that that we want to target. So if we uh, go through these computations, then what we find is that the TH power that we need to generate if we want to have a 50-meter link is about 6.3 watts. And if we assume 10% efficiency in our transmitter, that means we have to burn 63 watts in our transmitter in order to do a 50-meter link. Now, this is already a very optimistic assumption because we assume ideal loss. Now, in reality, there might be something like an object in the middle. It might be raining, which increases loss. So you can see that the amount of TH power that we need to generate at millimeter wave frequencies goes up dramatically. So to put this in context, your cell phone may generate something of the order of 250 milliwatts to 500 milliwatts, your cell phone. And it already speeds hundreds of meters. And here to get to 50 meters at 28 gigahertz, under ideal scenarios, we're already talking about 63 watts of power consumption. So clearly, this is not a very practical system for us. And what we see is that we are wasting power, right? We are radiating power in all directions. And this is very suboptimal. What we would, instead of trying to be like a bulb which is radiating light everywhere, we would prefer to focus the light in a specific direction, like a flashlight, right? And in that way, we need to generate less light, or basically less transmit signal, and we'll be able to increase the illumination on our receiver. But if we focus this signal to a specific direction, then we lose the ability to talk to other angles, right? So we need to then keep the transmitter and receiver fixed and then establish a link between them. But let's say for now that we agree to that condition, right? And in that case, what we are doing is we are sending more of the TH signal towards the receiver. So we can compare to the case where we were radiating in all directions. We can say that the received signal will be the TH radiated signal. It will be the TH radiated signal, the path loss that we see, and also an additive term which we call the gain, which is basically the focusing of the TH signal towards the receiver. Now, if we assume that there is 15 dB of this focusing gain, then we find that suddenly the TH power that we need to generate is only of the order of 200 milliwatts, which basically says that our DC power consumption will be of the order of 2 watts. So now we are starting to get into practical numbers, right? And if we assume that it isn't just the transmitter that is focusing energy in one direction, we also assume that the receiver is receiving energy only from a specific direction. So the receiver is also focused. So then what happens is that the gain of the transmitter and the gain of the receiver add up. So then what we find is that the TH power that we need to generate now is only 6 milliwatts, and DC power is of the order of 60 milliwatts. So now we find this to be an extremely practical system. We could build this, but the problem is that we have assumed that the THs and RHs are directional. They can talk only along a specific angle, right? And there is a fundamental theorem here which basically says that the more the gain or the more focusing that I do, then the smaller the beam width that I can achieve, right? So this basically means that you might have seen, for example, your cellular base stations where there are many antennas that are looking at different directions. Because again, what we are trying to do is be able to speak to all directions. We can either do it by having a single antenna that can radiate what we call isotropically or in all directions, or multiple high gain antennas, each of which is radiating in a specific direction. But what we would ideally like to do is be able to somehow combine both of these at the same time. So we would like to build a system where we can electronically steer the beam in whichever direction that we want, right? But at any given direction, once we select, we are able to focus the power towards that direction. So having an electronic capability to do that would be very useful, because mechanically moving this antenna around is not a viable thing in consumer applications, right? So is this a new thing to build an electronically steerable antenna? Not at all, right? People have been doing this for a long period of time, more than 80 years now. So if you look, this is one of the earliest papers published in July 1937 on an 18 megahertz 6-element array. And if you look at this picture, these are the antennas, right? So you have these large antennas, and these are working at 18 megahertz and building a 6-element array. Then as technology improves, so both our antenna technologies improve and importantly our devices get faster, we are able to increase the frequency of operation. So this is a 2 gigahertz array at 1960. This is an 8.2 gigahertz array in 2002, 64 elements. It's getting pretty compact. And this is an array that I worked on at IBM Research along with colleagues. And what this shows is a 16 element, 60 gigahertz receiver, where the IC occupies 6 millimeters by 6 millimeters of that ballpark. And then you have that connected to antennas, and the whole thing is about the size of a US quarter, right? So as technology has gotten faster and faster, we've been able to implement such arrays at really high frequencies. Now, this is not something that wasn't envisioned before. In fact, if you look at Gordon Moore's paper in 1965, in which he uh, proposed Moore's law, which has driven the semiconductor industry for 50 years. In that paper, right at the end, he actually says that if in the future people are able to make high yield integrated electronics, it will be possible to put multiple integrated microwave power sources on the same chip and build phased array antennas, and that could revolutionize radar, because at that time this kind of steering beam was very important for radar sensing, but now it's important even for communication because it helps us close link budgets. So hopefully at this point of time, you see the need for having millimeter wave arrays, because we see that we want to be able to steer the beam, but we want to be able to focus it, and that way we can reduce the amount of power that we need to generate. So the way that we do this is by creating or synthesizing wave fronts, right? So this is a high gain horn antenna. So the signal is preferentially radiated in this direction, right? But imagine that I emulated this by having multiple antennas. And in these multiple antennas, if I made sure that all these signals are in phase, then the signals will add up in this direction and they will destructively add up in other directions. So this creates like an interferometric pattern, right? And what we see is preferential radiation in a particular direction. What I can do is delay the signal going to some of the antennas. So in that case, this antenna sees a delayed signal, this antenna sees a less delayed signal, this antenna sees a less delayed signal. And what I can basically create is a wavefront where signals start constructively adding in this direction and destructive in other directions. So by being able to vary this delay, I can then steer the beam to different directions. So this is shown in a transmitter, but you can imagine by just reversing the arrows that this happens in a receiver as well. So in a receiver, what would happen is that signals would come in from different angles, but when they come in from this particular angle, they arrive at different antennas with a little bit of different delay, right? And then what I have is the signal at one and the delayed version of the signal at the other. And this delay is a function of the angle of incidence, phi1, right? And by introducing a variable delay in every element, I compensate for this so that they all align together, and then I sum them up. And when I sum them up, I get coherent addition. And so signals from this direction will be received. If I look for that setting signals from an undesired direction, what happens is that I am basically, my delays are not set up right. So all these signals don't add up in phase, they add up incoherently, out of phase. So then basically I get a small sum here. So I'm able to selectively receive signals from this direction while rejecting signals from other directions. So this is one aspect, right? But there is another subtle aspect here, which is that if I consider one of my elements and then I take all the noise that is in the element and input refer that noise, then what I can show is that when I'm doing the final addition here in the desired direction, all my signal adds up in phase, right? So since signal amplitude adds up, the signal power increases as n squared for n elements. But then if I consider my noise adds up incoherently. So what happens is that it only adds up as n, right? So if I look at my signal to noise ratio, I get an improvement. Or effectively, another way to say it is that if you have one path that is noisy, when you build an array of multiple paths, you also improve the effective SNR of the receiver, right? And in the case of a transmitter, these benefits can also be seen. So in the case of the transmitter, if you have a single element which is radiating a certain PTX and it has a certain efficiency eta, then the DC power consumption is PTX divided by the efficiency, right? And the radiated power is PTX times GTX, where you can say that GTX is the focusing of the antenna, right? But if I do this with n elements and I'm compensating in order to get the right direction that I want, then in the desired direction, each of these signals will add up in amplitude. So the power will go as n squared. So my radiated power will increase n squared. But I have n elements, each with PTX. So my DC power consumption only increases as n. So if I put a new metric, which is my system efficiency, which is how much radiated power I get for a certain DC power, I can see that that improves by a factor of n. So what we can conclude from this is that using a phased array or using an array that uh, splits the power required among multiple elements and multiple antennas helps in improving efficiency, and in the case of a receiver helps in improving signal to noise ratio. So knowing all this, we can now go and apply this into our link budget, right? And what we see from our link budget, which was originally, yeah, we wanted to get to 2 nanowatts, right? And what we now see is that if I have a single element and each element radiates about 12.6 milliwatts, and I use 8 elements in the transmitter and 8 elements in the receiver, I can close my link budget. And if I look at the overall power consumption, I see 12.6 milliwatts for one element, 10% efficiency, that is 126 milliwatts. I have 8 elements, so approximately 1 watt. So I have preserved the ability to steer my beam, and I have reduced my DC power consumption enough so that I can now have a practical link at millimeter wave frequencies. So the motivation here is to get this SNR improvement and the radiated power improvement without using fixed antennas, but instead be able to steer them while getting this uh, getting this benefit. So far we have said that we will build delays, or the signal at each element is delayed. And here the challenge becomes that if I want to really align the signals perfectly, what I need to build is tunable delays in each element. But building tunable delays is hard, right? Particularly building wideband tunable delays and the long tunable delays is pretty hard. So instead, what I do is I start making some approximations, right? And what is the approximation that I make? I firstly assume that the amplitude of the signal is varying very slowly with respect to the RF carrier, or I basically assume relatively narrow band modulation, right? And so I assume that A of t minus t naught is roughly A of t. Similarly, I assume phi of t minus t naught is roughly phi of t, right? And then that says that between this signal and this signal, there is only this extra term inside the cosine, which is effectively just a phase. So if I make this narrow band approximation, right, I can then say that I can do the combining of the two signals by just adding a programmable phase in each path. You can also treat this another way, which is that uh, if I want a constant delay across frequency, that's a linear phase across frequency. But I'm interested only in these frequencies. So instead of building a linear phase, I just approximate this by providing a constant phase, which is the value that is required here, right? And in this region, it will be okay. But as you make the, if you try to make the array more wideband, this approximation will mess up the operation of the array. So we've made this narrow band approximation, right? And so now we have translated the required variable delay in each element to variable phase. But now that we have said variable phase, is there any other benefit here? One very nice benefit of phase is, of course, that it's 0 to 2 pi, right? So I just need to generate 0 to 360 degrees variable phase. And it isn't that just because I want n times theta naught here, let's say theta is 30 degrees and n is 20, that becomes 600 degrees, and 600 is just minus 120, right? Modulo 2 pi. So I can easily build a 0 to 360 degree phase shifter and get the targeted operation. So given all this, what happens if we are doing this? Well, here is a linear array, which is n elements, right? And you can find out what the total output signal will be, assuming signal incident at different angles phi, right? And that basically translates to this function. It's effectively a sine nx over sine x function. But what it looks like is this. So we call this the array factor. So what this is saying is that if you steer the beam to a particular angle, like in this case, let's say I'm trying to receive at around 10 degrees, right? Then what I find is that this will be my array pattern. Signal, the settings will correspond to this, and any signal in other directions will be rejected. If I want to go change my direction, I change my phase settings, and I can now receive in this direction, or I can receive in this other direction, right? By just changing the phase settings. Important metrics here is how well can I make a null happen, because I might want to reject a signal from a certain direction. And the side lobes, which is that, sure, I want to receive from this direction, but if I plot this function, I see that it has these peaks in other directions, which are 12 to 13 dB down, right? So how well do I do in being able to reject my side lobes? So these are important metrics in an array. This is a plot on a linear scale here. This is the same plot, like a radar plot. and you can see that you can just steer the beam to different directions by varying the phases here and plotting and computing the appropriate function. And this is the beam steering that we are trying to accomplish. Now, I said variable gain, a variable phase, but in reality, if I want to push down these side lobes, because these side lobes I can imagine are only 12, 13 dB down, and I don't want to receive signals from the direction that this corresponds to. I only want to receive signals from my main lobe direction. What I can do is I can non-uniformly weight my array. So I can put variable gain as well. And now I can synthesize a pattern where, yes, my main beam gets broadened a little bit compared to this main beam, but my side lobes get attenuated a lot. So there is a lot of research just in pattern synthesis, right? How to set these weights and phases. But broadly, from a circuit designer's perspective, what we see is we need variable gain and variable phase in each element. So to summarize where we are so far, we have seen that millimeter wave link budgets are very challenging because of this phenomena of path loss, where loss is proportional to inversely proportional to frequency, since loss increases with frequency because loss is inversely proportional to wavelength, right? So what we have from a system perspective, the solution to it, we say, okay, we will take many elements and we will combine them together to build a transmitter. And similarly, we will take the many elements and combine their signals together to build the receiver, which will both improve our efficiency, improve our SNR, and help us close the link budgets. And we build a narrow band approximation to make our circuits easier because we don't want to build a variable delay. Instead, we want to build a variable phase shift. And what we also see is that we would like to have variable amplitude and variable phase in each element also, so that we can synthesize any particular pattern that we want. So now that we've done this, we can look at some transmit and receive beamformers, right? And what is it that is attractive about implementing these things in silicon? The key benefit here is that as technologies have gotten faster and faster, we are now able to build millimeter wave circuits in CMOS and BiCMOS technologies. But what is it that we can really use about these technologies? The key thing here is that the incremental device cost is zero, right? We can throw transistors at any problem, which is perfect because we are already talking about building multiple transmitters and receivers which require multiple circuits. But that's the kind of thing that we can build very well in integrated technologies. The other thing is that we can have very short interconnect length and very repeatable interconnect length. And where that helps is that we can start doing new architectures where we don't have to rely on purely power matched circuits or the traditional microwave way of doing it. We can do it the way that we design analog circuits, right? We can use some of those techniques. So now that we want a variable phase shift in each path, right? What we see is that we can implement this variable phase shift mathematically in different ways. So again, these are the benefits of integration because all these architectural explorations are possible with integrated circuits because every path is well matched. So what we can say is that instead of implementing this in the signal path at RF, because we would have to build a phase shifter at RF frequency, we could move it to IF frequency, right? And mathematically, this would all work out. But in this case, instead of having one mixer, we would have two mixers. Sorry, do you want me to stop sharing and try that again?
Yes, sir, if you can do that.
So, when did they stop changing?
Sir, what slide are you currently sharing? Currently, it is like you are not sharing anything right now.
Yeah, I stopped sharing it because I just thought
Okay.
I'll restart the sharing.
Okay.
So Sorry, now all of a sudden it is not. Are you able to see now?
Just a minute. Yes, sir. I'm able to see your slides. It's our array architecture, LO path / digital.
Yeah.
Array architecture
So,
signal path.
so did it stop way before or?
Yeah, I guess I was not able to see this slide. Isha, can you please confirm?
Yeah, I'm able to see it. Maybe there is an issue at our end.
Okay.
Now there.
Correct.
Thanks, sir.
Okay, so we have this phase shift that we need in each element, right? So if we uh, have this phase shift that we can implement at RF, or what we can do is implement it at IF over here, right? Mathematically, these two are the same. Only in this case, there's one mixer. In this case, there are two mixers. So the trade-off becomes, should I have multiple mixers and the associated LO distribution, or should I implement this phase shifter at the highest frequency in the system, right? And these architectures were explored a lot in the early versions of phased arrays, right? You can also show that instead of implementing the phase shift at IF, I can now implement the phase shift in the LO path. And if I implement the phase shift in the LO path, then I don't have the phase shifter in the signal path at all, which is very advantageous. The LO operates only at one frequency, so I need to just optimize my phase shifter at a single frequency instead of considering signal bandwidth, right? Alternately, the holy grail is to do digital beamforming, where I just down convert each path and then go and digitize right at the end, right? And build virtual, I can implement phase shifts in digital and combine signals from different elements. The disadvantages here are related to the fact that you'd have to have multiple mixers and ADCs. And so in terms of power consumption, where people have sort of settled on, and now that this design is quite mature, RF path phase shifting has emerged as a pretty well settled way of doing phased arrays, right? And if I want to build this phase shifter at RF, I can have multiple topologies for this phase shifter. You can see the slides. I just want to make sure.
Yes, sir. I'm able to see your
Okay.
slides.
Okay. So with the switch type phase shifter, the idea is quite simple. In this case, what we are doing is that there are two paths. One is a longer path and one is a shorter path. So we are switching between them. And by switching between them, we are basically changing the phase shift between input and output. And I can have multiple bits of this. So I can have one bit that decides 0 and 180, one bit that has 0 and 90, one bit that has 0 and 45, so on and so forth. So I can cascade these switch type phase shifters one after the other. That I'll take this question at the end of the talk because it's fairly complex, right? And one trade-off here is that these phase shifters, in the case of switch type phase shifters, each bit has to be implemented separately. And what this means is that there is a trade-off between the resolution and the number of stages that we build, and hence the area that we build. But the advantage is that it is passive, right? So it is going to be very linear, so we don't need to be worried about the distortions introduced by the phase shifter itself. Now the switch type phase shifter, the one very popular type of switch type phase shifter is what we call the bridged T-type structure. So in this case, there is a switch here and the switch bar is over here. So if you imagine the switch enabled, then there is a short between this port to this port. These two capacitors are over here and there is this inductor, and this switch is open, right? And so you see the switch off and this LP, right? So if these two resonate out, then this is a high impedance. So you effectively see a signal flow directly through our switch. But in the case where this V switch is, this path is off and this path is on, this inductor is shorted out. So you have this L1, C1, C1. So you can hopefully see a T-type structure here, which is C1, L1, C1, right? And so by applying these equations for L1 and C1, you can now get a certain impedance Z naught and a certain phase shift theta, right? You have a CLC structure. So this approach works quite well. And one challenge here is that it can be lossy as you go. Each of these stages can have some loss because signals are going through switches. So instead of doing it this way, where you have your RF amplifiers followed by your RF phase shifters, it's useful to do something like this where you have amplifier, some phase shift bits, some more amplification, some more phase shift bits, because the way what this does is that this distributes the losses in between. So while this is the lowest noise approach because all your gain is upfront, this approach balances noise figure and linearity. So this work was done at UCSD as a demonstration for how to build switch type phase shifters. And typical numbers that you can see here is that at 28 gigahertz, the loss is about 7 dB. If you consider 60 gigahertz, the loss is about 14 dB. And you can, in general, see that as you keep growing up in frequencies, depending upon the quality factor of the components available and the architecture chosen, the losses can get pretty high, particularly as we go to higher bits and higher phase shift range. So given these issues with switch type phase shifters, we can think about another architecture which we call the reflection type phase shifter. And in a reflection type phase shifter, the idea is that there is a quadrature coupler. So that is the signal goes from input to output. And what we have over here is terminations on the through and couple port. So we can think about a signal going like this, getting reflected and coming back out. And similarly, the signal going here, getting reflected and coming back out, right? So in these scenarios, when the input signal is here and it is hitting the reflection over here, the value of the reflected signal depends upon the impedance of the termination, right? And so by varying the impedance of the termination, we can vary the effective signal that comes out at the output. And we can actually get both amplitude and phase variation by varying the magnitude and phase of gamma t, right? So this is one approach. And in this approach, we use a coupler, and then the resolution depends upon and range depends upon how much we are able to vary this load. So one way to think about this termination is that we are varying this termination around a Smith chart, and we want to get gamma, we want to get full 360 degrees phase tuning, then we need gamma to vary all over the Smith chart, right? And we would like low loss, so we want gamma to be along the unit circle. But in reality, if we put down a variable capacitor, we are going to get a certain range. And gamma is going to have a certain amplitude less than 1 depending upon the quality factor of the capacitor. So what we see is that we see some losses and we see limited phase shift range. Instead of doing just a C, you can build a more complex structure, which is a C1, L1, C2. And by building C1, L1, C2, you can enhance the range, right? And what one can show is that one can get more than 180 degrees tuning range. I start along this circle, right? Each of these circles is basically C1 varying for a given C2. So first I keep C2 min, I travel on this circle, then I move to C2 mid, I travel on this circle, then I move to C2 max and I travel on this circle arc, and basically I've gotten more than 180 degrees phase shift. So I can use this kind of load design to get 180. And we have built these kind of reflection type phase shifters at 28, at 60, at 94 gigahertz. And we can basically show that we can get 180 degrees of phase tuning with about 6 to 7 dBs of loss in the system. And with more complex design of the CLC loads, what we have also shown that you can get a full 360-degree tuning with about 7.5 dB loss at 28. Of course, that more complex load is possible because we are able to operate at a somewhat lower frequency where the parasitics are less, right? But as we go to really high frequencies, we have to reduce phase shift range. So overall, we see that these are two approaches of building passive phase shifters, which are very linear. But we can also do active phase shifters. And in active phase shifters, the approach is that we have an input quadrature coupler, we get 0 and 90, and then we can put variable gain on I path and Q path and sum it up with sum it up. And when we sum up I and Q signals with different weights, we can create a vector in any direction that we want, right? So we basically can get any amplitude and phase inside this circle. And the flexibility of an interpolator can be quite useful. The challenge is that these are active circuits, so they have noise and they have linearity issues, right? We build them in a similar way to a Dilbert type mixer or a multiplier. So we effectively have the I and Q signals, and then we can weigh them differently by changing the bias control, right? And by doing current steering, we apply variable weights to I and Q, and then we sum them all up together in this RF node in the current mode, right? And by doing this kind of interpolator, we can get again full 360-degree phase, full 360-degree uh, uh, tuning range. Sorry, I didn't understand the question. Right, maybe I'll just keep going, and then at the end we can unmute for questions.
Yes, at the end we will take that question. Yeah, sure.
So overall, we have seen a passive phase shifting approach and an active phase shifting approach, and you can combine, mix and match them, the way for different application. For example, we can have a passive 180-degree phase shifter, which is reflection type, and get the remaining 180 degrees with a phase inverting amplifier. So it switches either, it's an active amplifier that either provides the 0 output or the 180 output. Alternately, you could build a switch type phase shifter here to decide between 0 and 180. So it is possible to combine different topologies based on needs, but broadly speaking, active and passive is a good trade-off to think about. There's one other very important benefit of passive, which I should mention, is that passive phase shifters are bidirectional. So it doesn't matter whether you're looking from input to output or output to input on this side, right? So they can basically serve as both your TH phase shifter and RH phase shifter, depending upon how the transceiver architecture is done. So we have built the passive phase shifters and vector interpolators, active phase shifters. The other key component that we need in the system is signal combining. And the standard way in which we do signal combining is a Wilkinson combiner. We can, instead of building a distributed Wilkinson combiner with quarter wave transmission lines, we can instead build a lumped model for that equivalent for the Wilkinson. And the Wilkinson is typically pretty wideband, so it's usually the combiner of choice. Of course, we can build an active combiner too by taking two inputs and then adding their currents together. The one trade-off in this from a system design perspective is that if I take a Wilkinson splitter, then I might have a situation where my first amplifier in my TH particularly drives a signal that gets split, and then it drives the next two amplifiers and so on and so forth. But when it does that, the effective input power here is 3 dB less. So I need to make sure that this amplifier A has enough OP1 dB to drive so that it doesn't start dominating the overall signal chain compression. So you can imagine a situation where if you have 8 elements and you're dividing the power 8 ways, then this amplifier has to drive 8 paths. So if each path wants X, it has to provide 8 X, and which might be too much. So then in that case, what we do is we consider we do this signal chain linearity analysis, where we assume that each Wilkinson has some extra loss, not just 3 dB. It has 4 dB, 1 dB extra loss, and we consider the linearity of the total signal path. So in this case, you can see is that as the signal is split, so this is a 16 element array. My original amplifier OP1 dB might be high, but now my total OP1 dB is dropped to 0. minus roughly 0 dBm. So this purely passive distribution can be a problem. So what we do is we end up with some active distribution stages. So the idea here is that there is some input, and then we do a cascade stage, which is effectively splitting the current, and then it drives two outputs. So this is an active splitter stage, right? And the dual to that is an active combiner stage, where we take two inputs, we then sum up the currents and drive a common output. So we can have active splitter and active combining stages in the transmitter and receiver. Finally, there's this approach can also be combined in practice by taking advantage of some of the physical distribution of signals that you need on the IC, and trying to implement your combiner to incorporate that signal distribution. So those kind of approaches are also done for compact area. So what we then do is we can define a metric, and here we call this eta A, right? And what this metric is basically calculating is if I had n elements in the array, and if each of my receiver element had a noise figure of f, then I would have expected my entire array to have a noise figure that is f over n, right? So effective noise figure that is f over n. So what this measures is how close that you get to it. So a number 1 is of course ideal, but if we have losses in our combining network and they introduce noise, we can see that our SNR of the array is not n times the SNR of the front end, it's somewhat less. And we can capture that using this array efficiency factor, so to speak. And depending on that, start inserting active combining stages in the middle. So practically, how do these systems look now? So we've started building in academia and industry. There's just been a lot of demonstrations of very large phased arrays. I've picked some representative examples. These are not the largest. These were not the first, right? But they just have some interesting data points in there. So this is a paper that came out of Broadcom in 2014, where they built a 16 element TH, 16 element RX. You can see that the phase shifting is happening in the RF path. They have separate phase shifters for TH and RX. The one very nice idea here is that there is just a single interface into the IC, and that includes the LO reference, the IF signal, as well as the control signals, which are all placed in different frequency bands. And by just sharing the cable, this makes an interface that is going to the 16 element array very simple. I need only one cable, and all the information is multiplexed in that frequency multiplexed in that cable, right? And if you see what the overall system looks like, so you have the 16 elements, flip chip packaged to antennas, and this is what the whole module looks like, with a separate baseband IC and a separate phased array 60 gigahertz IC. Shows some measured patterns demonstrating beam steering, and we can see that we can leverage the really wide bandwidths at 60 gigahertz to get multi-gigabit per second links of the order of 4 to 5 gigabit per second. This is another example of an array, and this the idea was that to build a scalable array. So the idea is to have a unit cell that is repeated. So this has 4 of these ICs inside it, and each IC is 16 elements. So this is a 64 element array tiled with 4 ICs. And the way that the ICs are constructed, we can put 4 of them next to each other to build a large array. So each IC has some elements, and then we combine ICs together to build even larger number of elements, right? And this scalable concept has been generally adopted now, and most of the arrays that you see are scalable arrays where a unit tile is tiled to build large arrays. And the other approach here is the compact area to fit a 94 gigahertz transmitter and receiver all into a very small space. So that leads to a lot of architecture optimization as well as circuit optimization. This circuit used passive phase shifters, and what we can see here is one element occupies only about 1.5 millimeters by a millimeter, so in that range. And with very compact elements, we can fit a lot of elements into the IC and be able to build a large array. So in terms of state of the art, what we see now is that people are building extremely large arrays, which are all tileable. RF path phase shifting is probably more dominant than other approaches. And array frequencies, of course, now go well beyond 100 gigahertz demonstrations. So in this context of arrays, where for the first 15 years we have been building these phased arrays, I've been involved in several of these demonstrations at different frequencies. But what are we going to do next? Well, the key observation here is that with a phased array, we are building out of many one system. So we are taking all these n element signals and combining together and producing one output. But in reality, what we are seeing is systems where signals can come in from many directions, or we are basically having signals where we could be operating at different bands at the same time. So we are actually, phased arrays are very inefficient in the sense that we are throwing away spatial information. So what we would ideally like to do is build MIMO arrays where we can receive narrow beams, but multiple narrow beams at the same time. And the standard way to do this would be to do this in the DSP, where we receive signals from all the elements and we combine them together to form multiple beams. And what are the challenges here? There are multiple mixers, so all the LOs need to be synchronized. There are multiple ADCs, so we need to make sure that this interface over here is simple so that we can get data into the DSP. We need a low-cost antenna to IC interfaces, right? But there is one downside to doing digital beamforming, and that is, in this case where I'm doing the spatial combining prior to the ADC, I'm actually rejecting the jammer. So let's imagine that the jammer is in red. I'm rejecting the jammer spatially. So the array is providing me spatial filtering. And I'm rejecting the jammer before the ADC dynamic range requirements are reduced. But if I consider this approach where I'm doing digital beamforming, the jammer is there in every element, and the jammer rejection happens in digital. So this ADC still needs to be able to work with a very strong jammer signal, which drives up the number of bits, which drives up its power consumption. And I have n of these ADCs as well. So are there energy efficient architectures that we should be thinking about for building MIMO arrays? Or is it just taking a single receiver and just duplicating it n times? Is it as simple as that? So before we get into this, we should talk also about, in general, RF arrays as well, where given the bands of operations that are of interest, what we would like to build is circuits that are reconfigurable, that can be operating at different frequencies at the same time. And one general approach to build reconfigurable networks is through this concept. It's a very old concept of n-path circuits, but basically the idea is that you have n networks, and then you are commutating the signal to each of these, and then getting them back. And this, of course, is well suited for CMOS because we are, switches and clots is basically what this is. And what we find is that by doing this, we can synthesize many different networks or network functions that we would like to do, right? So what we can think about broadly is that a signal has certain properties. It is at a certain time, it's at a certain frequency, it is coming from a certain angle, it might have a certain code modulated on it, the signal is occupying a certain polarization. So in all these things, what we would ideally like to do is have a receiver that can work in this electro space and start rejecting signals based on some properties and selecting other signals based on some other properties, right? And those properties, we think about filtering in frequency, but we can talk about filtering in space. We can talk about filtering in code. So we can have this generalized electrospace filtering, and then in the context of MIMO, where our receiver has actually multiple elements, and these multiple elements are together selecting and rejecting some of these properties. So if we take a spatial example of this, what we are talking about is that there is this MIMO receiver, and what we would like to do is have this MIMO receiver work in some way such that at each element we create a spatial null which takes out an interferer. So the interferer is in this direction. Imagine that I could somehow put a pattern here at the antenna, or I could make an antenna that had a reconfigurable null that could be steered to take out this, and then I take the rest of the signal and I provide it to my digital beamforming. So this is very useful because I am able to form beams, still multiple beams in the digital domain, but I'm doing my filtering or taking out the undesired signal in a specific direction. So what I'm now building is no longer phased arrays, but I'm building nulled arrays, which have a certain null, and the rest of the phased array beamforming or the multi-beam forming is done in digital. And of course, we'd like to extend it. We don't just want one notch. We want multiple notches. We want them to be able to steer them in angle. We want to be able to steer them in frequency. So what does the whole picture look like? Well, there is a multiple antenna system. It has a MIMO filter up front, and this MIMO filter is rejecting this frequency and a specific angle, and then I digitize the rest of the signals. I do my digital signal processing, and I have my MIMO beams. So I get my MIMO beams, but my ADCs also don't see the jammer. So that's basically the idea here. How do we build this? Well, we can build this using some of these n-path circuit concepts and mid-sync concepts. I'm just going to show some results in the interest of time. But what you can see here is a receiver that we built where there are notches. So this is a notch at 500 megahertz. This is a notch at 700 megahertz at these angles of incidence. And I can, by changing the frequency of the clock going into my filter and by changing weights, what I can do is I can steer the null. I can keep one null at the same frequency and angle, and I can move the other null to some other frequency and another angle. So this is basically effectively like building an antenna with a variable pattern, right? And these kind of approaches, again, work for MIMO-spatial or MIMO-spatiospectral filtering. Similar concepts can be extended to millimeter wave, where here the idea is that I have a 4-input MIMO system. I'm going to, instead of putting 4 paths in each to downconvert each of them, I'm instead going to downconvert them in a different way so that at each IF frequency, I have 4 IF frequencies. At each IF frequency, I get a different sum of these signals. And by then adjusting the weights of the signals in each of these sums, I can create patterns at each of these frequencies, IF frequencies. So for example, F1, I can say is receiving this pattern. F2 is receiving this pattern. So each of these patterns has one particular null. So I'm simultaneously receiving 4 different patterns. Each of those 4 patterns has a different null. So it's rejecting a different interferer potentially. So I can build MIMO filters before going into my digital. That's basically the philosophy. And we can extend this even further, where we now say that I want to be able to do these reconfigurable nulls, but I want to do this not just at one RF frequency, but at 2 RF frequencies. So here we pick 28 and 39 because those are 5G bands. And what we show is that we can create beams at each IF frequency that are either pointing in a certain direction. All 4 beams are pointing at different directions at 39, or a situation where there is one beam that is receiving 28, another beam that is receiving 39, right? So we can mix and match the beams to look at different frequencies, have different spatial nulls. So we are not thinking about what is happening in analog as a selector, but rather as a rejector, and then do the beam forming and the multi-beam processing in the digital domain. So to conclude, what are arrays of the next decade going to look like? Firstly, we feel that MIMO and digital beamforming arrays will be where we move towards. But in order to lower their power consumption, we will be implementing spatial filtering. Again, we have looked at IF, RF, so where we implement the spatial filter will be an area of research. The other area of research that is still an important issue is that the millimeter wave IC we can build with very low cost, but packaging this array of ICs with antennas still remains a very expensive proposition. So this is something that will be an area of research, how to package arrays of ICs with antennas with low cost and good performance. And finally, we will see, of course, a move to higher frequencies in all these arrays as we find new applications in sensing, particularly emerging in those areas. So thanks very much for your attention. Happy to take questions now.
Okay, I will just thank you so much, sir, for such a wonderful presentation. I see there are 2 questions in the chat box. First, we will take those questions, and after that, we will ask participants to unmute yourself if they have any questions. So the first question that we have is why people use true time delay circuits if phase shifter approximation works. Do we really need true time delay circuits if modulation signals have smaller bandwidth compared to the center frequency?
So there are so this is a question that should have a quantitative answer, right? Because it depends upon that particular application. But in general, I would say that at millimeter wave, true time delay circuits are not that necessary. The bandwidths of interest are narrow band enough, or the modulation bandwidths are narrow band enough that phase shift approximations work well. If we have fractional bandwidths that are exceeding, well over 15%, numbers like that, 10, 15%, then we need to start thinking about building true time delay circuits. The other note also is that with true time delay, one doesn't get this modulo 2 pi benefit, right? So if I have a 10 picoseconds and if I have 16 elements, then I need 160 picoseconds in my last element, right? So building such long delays is quite non-trivial, right? So in general, I would say there are some problems that happen because of this phase shift approximation. So one way to think about it is that what happens is that if you think about your array, it is pointing in one direction at your center frequency, but at frequencies well away from your center frequency, it might be pointing in a slightly different direction, or you might get this phenomena that is called beam squint. But those are quantitative things to evaluate. But I would say in industry, the first preference is to see if a phase shifter is sufficient, and in most cases it is.
Correct. Yeah. Thank you, sir, for that for the answer. Now, the second question that we have is, how do we take care of the interference between the two transmit path or the true receive paths, since the interference increases at as we go in at higher and higher frequencies like millimeter wave?
So if by interference, do you mean the coupling between the two paths? So, you are transmitting in one, so they crosstalk with each other, right? That's basically, yeah. So this is a good question. So there are two aspects to this. The first aspect is that in a phased array, I'm effectively assuming in a transmit version of a phased array, I'm effectively assuming that the signal at all these elements are the same except for a carrier phase shift between them. So there is coupling between them, but that doesn't necessarily uh, I can think about an effective signal that is generated, which is the sum of my desired signal plus the leakage signal, right? Because both these signals are quite similar to each other. So in that case, what I do is I try to compensate for that coupling in some way, right? But the primary coupling mechanism is actually through the antennas, because the antennas are not isolated from each other. And what one also sees in practice is that when I'm steering towards this end of the handles, right? When I'm steering towards the end fire, then the coupling between the antennas can increase. And what happens is that at that point, the array the pattern is no longer predictable with this equation, because there is just a lot of coupling between elements, right? So one can compensate for it a little bit, but it actually creates many interesting problems. One of which is that this coupling effectively causes the impedance that the transmitter sees to change. So the antenna is no longer a constant impedance. The antenna impedance that I see depends upon the angle in which I'm trying to radiate. And if I'm designing a PA, then the load impedance is changing. So this becomes like a VSWR problem, a VSWR problem in the PA. So now my PA is no longer seeing the optimal load that it was designed for. So that creates problems. So antenna coupling is a big problem, which basically, if I go beyond minus 60 degrees, I just start seeing my pattern degrade severely from what it should be, right? The array coupling is a big problem. What I do to reduce it, so on the chip, we do all the things that we do usually. We do transmission line based distribution, spacing of inductors. We do all that to reduce the coupling between the paths. On the antenna design itself, we try to design antennas with low cross coupling between them, right? So The problem, however, is coming from the antennas primarily, not coming from the ICs usually.
Okay, yeah, understood, sir. Well, thank you so much. Pushpiyadan, sir, can you please unmute yourself? You have a question, right?
Yep. Sir, I
Yeah.
wanted to ask you one question regarding the amplitude variation with respect to
Yeah.
the phase, different phase tuning settings.
Yeah,
So,
it's a
be
good
it
question.
like any phase shifting architecture, be it reflector type phase shifter or IQ interpolator, if there is an amplitude variation for different phase setting, how will it affect the overall phased array performance?
So good question. So I think I'll sort of explain it with this plot, right? Because what this plot basically shows is that uh, if I want to look at a constant phase point, the amplitude changes, or if I look at a constant amplitude, the phase is not uniform step size, right? So my amplitude and phase start coupling in terms of settings. When I change my phase, I change my amplitude. Uh, you can reduce this by design. So there are a couple of approaches. Recently, there has been approaches where in this type of interpolator architecture, we start degenerating this transistor, right? And what we can show is that by degenerating this, we reduce some of the dependencies and reduce the variation. So so there's some circuit design techniques. In the case of passive, the one philosophical circuit design technique is that um, if I think about, actually, if I broadly think about this as some interpolation between 0 and 90, I can think that instead of doing just 0 and 90, I start interpolating between 0, 120, 240, and 0, 120, and 240. So I interpolate between three vectors and not two vectors, right?
Okay.
So by using three vector bases or four vector bases or six vector bases where I'm using differential signals of 0, 120, 240, I can pick points that are that have less variation.
Okay. So can we
But
say that that the LO phase shifting architectures are less prone to this amplitude variation? Like,
very good point. That's yeah, I was getting to that in RF phase shifting or IF phase shifting, this is a standard problem.
okay,
And LO phase shifting is less sensitive to it, right? Because it's not sensitive to mixer amplitude.
right,
So that problem goes away in LO phase shifting, but then we have this LO distribution problem still.
right.
Yeah.
Understood. Thank you, sir.
Where industry has gone in general, though, is that we build large RF arrays and we do RF phase shifting, and we effectively design the phase shifter to be fairly uniform, less than 1 LSB of variation across, less than 1 dB variation across phase shift, right? And with that 1 dB variation, usually you can live with the array. It's not like a dominant source of loss, a dominant
Okay,
source of degradation. If I see the reflection type phase shifter by design, I can get to like the 1 dB number basically.
right.
So yeah, that's usually like a spec that people are able to meet now by just careful design.
Okay.
Yeah. Thank you, sir, for the answer. Guys, any more questions from the audience? Please raise your hand. We will unmute you. We'll just take few questions and we will wrap up the session. Anyone has any questions? Okay, looks like nobody has any questions. I will just ask one question to you,
Sure.
sir. So, like, how are the phase noise requirements at the 28 gigahertz frequencies? Are they too stringent, or like what about the PLLs that we build in the on chip? So, like, are we able to build the PLLs at millimeter wave, or we are doing some kind of frequency multiplication architecture? And if we are doing it, then how are we taking care of the phase noise issues?
So I don't have the exact spec in mind, but the architectures, integrated VCOs with maybe a single doubler, right? Or at most a quadrupler work fine at for 5G. So there are PLLs implemented in CMOS and silicon germanium bipolar that work. The metric is really in terms of EVM. I don't have the exact jitter number. It's of the order of sub 100 femto, but you can see at ISSEC that people have implemented both for 60 and 28 PLLs that meet 5G specs in CMOS. And then usually fundamental VCOs at about 10 to 12, and then you have a doubler going up.
Okay, sir. Okay. Thank you for the answer. Audience, if you don't have any questions, then our chapter chair Anand Kumar will give a thank you note to Professor Arun. So I will just wait for 10 seconds. If you guys have any questions, then please raise your hand, or else we will give a thank you note to Professor Arun. Okay, so there are no questions from audience. So Anand, please go ahead and please present the thank you note for Professor Arun for such a wonderful talk. Anand, you are on mute.
Yeah, am I audible now?
Yeah, you're audible.
Hello. Yeah. Yeah. Thanks, Om. Thank you, Professor, for taking the time and effort for the talk. I can say this on everyone's behalf that the talk was very interesting and informative. Thanks again, Professor.
Thank you very much for the invitation, and like I said, great effort and good luck going forward.
Thank